The definite integral. Let's revisit how to find the approximate area under a curve using n rectangles. So the fundamental question is, if we have some function f of x between x equals a and x equals b and the x-axis, there is an area enclosed here. And we've already discussed approximating that area by taking this region here and dividing it up into n parts. If we do that, we're going to get n rectangles, and we can find the areas of those rectangles by multiplying the length of the base of the rectangle by the height of the rectangle. Now, previously, we have discussed getting the height of the rectangle by using the left or right endpoint. But actually, you don't have to use the left or right endpoint. You can use any point in that subinterval. So, for example, you can see here in the picture that the height of the rectangle is located here, and that corresponds to some x value on the x-axis that I'm going to call x1 star. So we call that x1 because this is the x value corresponding to the height of the first rectangle, and the star indicates that it is the chosen x value of all the x values that we could have used between these 2 points. You can see that the second rectangle here has a height corresponding to this x value, and we'll call that x2 star. And so on down the line. The next rectangle has a height here, and that corresponds to this x value, which we call x3 star. And if we have n rectangles, by the time you get to the end of this, the last rectangle will have an x value xn star associated with the height of that rectangle. So remember, the way we calculate the approximate area under the curve is we add up the areas of all of these rectangles. So we are going to take the height of the rectangle, so in this case here that is f of x1 star, and we're going to multiply that by the width of the rectangle, and we call that delta x. And then we do that for the next rectangle, f of x2 star multiplied by delta x, and we do this all the way down the line until we get to the last rectangle, which has a height of f of xn star and a width of delta x. So nothing here has changed from our previous discussion, except for the fact that you don't have to use a left endpoint or a right endpoint. You certainly can, but you can use any point in between the left and right endpoints as well. So these values of x that we are going to call arbitrarily xi star simply correspond to some value between the left and right endpoint. Now, the main reason I bring this up is because the sum that you see here representing the approximate area under the curve, this is a special type of sum called the Riemann sum. And we can use a special notation called summation notation to abbreviate this sum, like so. So what we want to do is really get to be familiar and comfortable with this notation. When you see a summation symbol like you see here, and a f of xi star times delta x, you should just think of this as f of xi star is the height of some rectangle, and delta x is the width of the rectangle, or the base of the rectangle. And when you multiply those together, that gives you the area of that rectangle. And then the summation symbol just means that once you find the area of each of these rectangles, you are going to add them up. And so literally this symbol here just means you're going to add up all of these f of xi stars multiplied by delta x. So again, the sum that you see here is called the Riemann sum. Now, one final thing to discuss here is that when you use this technique to approximate the area under a curve, you need to realize that if your function goes below the x-axis, when you find the heights of these rectangles, they will show up as a negative number because the function value is below the x-axis. And so because the height of the rectangle is negative, that will make the area of this rectangle negative. And so when you're finding the area between the curve and the x-axis, any area above the above the x-axis will be counted as a positive area, and any area below the x-axis will be counted as a negative area. And so when you do this process, you are going to end up getting a net area. That is, you're going to have the positive area minus the negative area. And that total area could come out to be a positive number or a negative number, depending on whether there is more area above the x-axis or more area below the x-axis. Now, in many cases, you will have situations like the one that you see here, in which case all of the area is above the x-axis, in which case it is counted as a positive number. But just know that when you're using Riemann sums to find the area under a curve, that area can sometimes be a negative number. So let's go ahead and evaluate the Riemann sum for f of x equals x cubed minus 6x for x between 0 and 3 with n equals 6 subintervals and taking the sample endpoints to be the right endpoints. So in other words, we want to find the area under the curve, or at least approximate the area under the curve, using 6 rectangles and taking the right endpoints to give us the height of each rectangle. Now, the truth here is you don't actually have to have a graph of the function to be able to do this. You really only need to focus on the number line. So let's take a look at a number line. And I'm just going to focus in on the part of the number line that is relevant to us, and that is the number line from x equals 0 to x equals 3. We're going to divide up this interval from 0 to 3 into 6 equal parts. So the first thing I need to do here is calculate my delta x. Let's recall from previous sessions that delta x is b minus a divided by n. And for us, that means it is 3 minus 0 divided by 6, and this is equal to 1/2. And this means that every 1/2 unit starting from 0, you will have a subinterval. So allow me to put down 1 and 2, and then if we break that up into halves, you get these numbers here. So you should be able to see now we have 1, 2, 3, 4, 5, 6 subintervals. So when we go to do our Riemann sum for this, our xi stars are going to be the right endpoints. And the right endpoints of all of these intervals are these 6 numbers. Right? So remember, on the first interval here, the left endpoint is 0, the right endpoint is 1/2. So 1/2 is the right endpoint of the first subinterval. On the next one, 1/2 is the left endpoint and 1 is the right endpoint. So we're going to use 1 for the next one. So literally we can assign numbers to these. So x1 star would be 1/2. x2 star would be 1. x3 star would be 1 and 1/2, which is 3/2. X4 star would be 2. X5 star would be 2.5 or 5/2. And the last one, X6 star, would be 3. So again, that is just these 6 numbers, and I'm assigning a subscript to each one. So again, for example, X4 star equals 2. That is because 2 is the right endpoint of the 1, 2, 3, 4th rectangle. Now, I know you don't see any rectangles here, but you have to imagine if you had a function here, you would have rectangles drawn up to that function, like you've seen in previous examples. So to compute the Riemann sum here, in this case, we are going to take the sum from I equals 1 to 6, f of xi star times delta x. And so in this case, that is going to be f of x1 star times delta x plus f of x2 star times delta x plus f of x3 star times delta x plus f of x4 star times delta x. And we keep going, just a couple more here, f of x5 star times delta x. And finally, f of x6 star times delta x. And so just so we make sure we understand the notation here, when we say I equals 1, that gives you the starting value for I. And up here, the 6 gives you the last value for I over here. So now for us, these values are, well, x1 star is 1/2, so that's going to be f of 1/2 times delta x. Delta x is also 1/2. Plus f of x2 star is f of 1 times 1/2. And so on down the line. We're going to plug in the rest of these numbers. Oops, and let's go ahead and say delta x is 1/2. And the final one here is, well, that should be f of 5/2, and this should be f of 3 times 1/2. There we go. All right, next we have to find all these function values. So we have to compute what is f of 1/2, what is f of 1, f of 3/2, etc. And so for this, we have to go to the function. So let's keep in mind the function is right here. F of x is x cubed minus 6x. So let's figure these out. F of 1/2 is going to be 1/2 cubed minus 6 times 1/2. And this is 1/8 minus 3, which is 1/8 minus 24 over 8, which is negative 23 over 8. F of 1 is 1 cubed minus 6 times 1. This one's a little bit easier. That ends up being negative 5. And we're going to do this for all of these values that you see up here. So let's go ahead and compute those. So here are those function values. Now we're just going to put those in each of their respective spots and multiply them by 1/2. Okay, so when we do all this work here, we end up getting negative 63 over 16. And this is the approximate area between the x-axis and the curve. Please keep in mind that any area below the x-axis would be counted as a negative area. So this definitely has some area below the x-axis. Now, you don't have to graph the function to be able to do this. That's what I wanted to prove here. But let's go ahead and bring in a graph to see why that area is negative. So here is what that graph looks like. So here's the function x cubed minus 6x from 0 to 3. And you can see there is definitely what appears to be more area below the x-axis than there is above the x-axis. And when we did that approximation, 4 of our rectangles had negative area and 2 of our rectangles had positive area. And you can actually see that right here in the calculations. You see how these first 4 numbers here are negative? That's representing each of those negative areas. and the last two are positive, and that represents the positive areas there. So it makes sense that our total area in the end ended up being a negative number. Now, this is nothing new. We did this in previous lessons. But the main point here is to just bring in this terminology of what it means to use a Riemann sum. So again, a Riemann sum is just this notation that we're using here. But really, it's the same thing that we did previously. Now let's discuss how we're going to find the exact area under a curve. So we're going to use the same principles. Suppose I want to find the area under this curve here. I'm going to break up this interval into n subintervals, and I will approximate the area under the curve by finding the areas of all of these rectangles and adding them up. And that is exactly what we are doing right here. But to get the exact area, you might remember previously that when you use more rectangles, your approximation gets better and better and better. So of course, the best number of rectangles to use would be an infinite number of rectangles. And so to get the exact area under the curve, I'm going to take the limit as n goes to infinity of the sum of all the areas of these rectangles. Or, using the Riemann sum notation, we are simply going to take the limit as n goes to infinity of the Riemann sum. And when you do that, you will get the exact area under the curve. Now, actually doing this and taking that limit is a pretty arduous process, and it can be really tedious. But conceptually, this is the theory. So now what I want to do is formally define what we call a definite integral. The definition of a definite integral is that if you have some function defined from x equals a to x equals b, and you divide it up into n subintervals of equal width, where delta x is equal to b minus a over n, and we let x0 equal a, and then we have x1, x2 up to xn equal to b, be the endpoints of these subintervals, and we let x1 star, x2 star, etc. be any sample points in these subintervals, so that xi star lies in the ith subinterval, then we define the definite integral of f from a to b to be this: the limit of the Riemann sum. And we know that this is the exact area under the curve, as we just discussed. Now, the notation for a definite integral is this symbol here. We use this elongated s, and then we put the limits a and b at the lower and upper ends of this symbol. So to read this, we would say we are taking the integral from a to b of the function f of x with respect to the variable x. And so the definite integral of a function from a to b represents the area under the curve from a to b. Now, because this is a limit and because limits sometimes do not exist, we have to say, if this exists, we say the function f is integrable on AB. Integrable means able to be integrated. Now let's just take a look at a few notes. The symbol that you see here for the integral was introduced by Leibniz and is called the integral sign. It is an elongated s and was chosen because an integral is a limit of sums. In the notation here, f of x is called the integrand. A and b are called the limits of integration, where a is the lower limit and b is the upper limit. For now, the symbol dx has no meaning. Dx simply indicates that the independent variable is x. don't worry too much about dx right now. The procedure of calculating this integral is called integration. Next note, the definite integral is a number, and it does not depend on x. In fact, we could use any letter in place of x without changing the value of the integral. So the integral from a to b of f of x dx is the same as the integral from a to b of f of t dt, or the integral from a to b of f of r dr. The variable of integration doesn't matter. And finally, this sum here, as I previously mentioned, is called a Riemann sum, and it's named after the German mathematician Bernhard Riemann. Now let's move on to some important theorems. The first theorem says if f is a continuous function, or if f only has a finite number of jump discontinuities, then f is an integrable function. That is, the definite integral exists. So most of the functions that we deal with are continuous functions. And so that means the definite integral exists for most of the functions that you will see. The next theorem, and this one here is a really important one. It says if f is integrable on AB, then the integral from a to b of f of x dx is equal to the limit, as n goes to infinity, of the sum I equals 1 to n of f of xi times delta x. Now, at first, this might look like a Riemann sum, but this actually is not a Riemann sum, because in a Riemann sum, this xi right here would actually be written as xi star. So let's remember, when you have an interval, xi star refers to some number in between the left endpoint and the right endpoint. But in that same interval, xi would be the right endpoint and xi minus 1 would be the left endpoint. So when you see the notation xi, that refers to the right endpoint. So this theorem is going to give you a way to actually calculate a definite integral by using the right endpoint. Okay, what is delta x? Delta x is still b minus a divided by n. And most importantly, right here, xi can be formulated by using xi equals a plus I times delta x. Now, as we work on some examples applying this theorem to do some definite integrals, you are going to find these summations here and these properties here useful. So I will bring these up in just a minute as we use them. Let's do an example. I want to evaluate the integral from 0 to 3 of x cubed minus 6x. Now you might remember that this is precisely the function that we approximated the area for just a few minutes ago using 6 rectangles on the same interval. However, now we are going to get the exact area, and we're going to use this theorem to do it. So we're going to use the sort of the Riemann sum, but without xi star, we're going to use xi, the right endpoint. So the first thing you need to do is identify all the important components of this problem. So in this problem, f of x is the function that you're integrating. This is this function right here, x cubed minus 6x. A is 0, b is 3. That just refers to the lower and upper limits, respectively. So what we need to do now is we need to find delta x for these values. Now, delta x is right here. It is b minus a divided by n. Well, b is 3, a is 0, but divided by n is going to stay divided by n. So there is no specific value for n here. And of course, this simplifies to 3 over n. Now we need to know, what is xi? Well, the formula says xi is a plus I times delta x. Let's remember that a is 0, so we have 0 plus I times delta x, and delta x we just figured out was 3 over n. So this is 3I over n. So now to evaluate the definite integral from 0 to 3 of x cubed minus 6x dx, I'm going to apply this formula. So we will be taking the limit as n goes to infinity of the sum I equals 1 to n of f of xi. Now, we just figured out that xi was 3I over n. So what is f of xi? Let's do that off to the side here. So f of xi for us is going to be f of 3I over n. But let's remember that f of x is x cubed minus 6x. So f of 3I over n, you are going to plug 3I over n in for x. So we get 3I over n cubed minus 6 times 3I over n. And if you do the math on this, this is 27I cubed over n cubed minus 18I over n. So that is f of xi, and that is what goes right here. So let's go ahead and put that in our summation. Now, in addition, we have to multiply f of xi times delta x, and delta x is 3 over n. So now this whole problem comes down to simply evaluating this sum. So let's go ahead and see what we can do here. We have the limit n goes to infinity. We have the sum I equals 1 to n. First thing I'm going to do is simply distribute 3 over n to both of these. So we're going to multiply 3 times 27, which is 81, I cubed over n to the 4th. Okay, so I'm multiplying top to top, bottom to bottom, minus, and then we have 3 times 18i, that's going to be 54i, divided by n times n, which is n squared. Okay, so that's just basic algebra. Now I'm going to use some of those properties of summations. So this property right here says that if you have the sum of ai minus bi, you can take the sum of ai minus the sum of bi. So right here, I have the sum of this thing minus this thing. I can do separate sums on each of those. So in a way, you can think of, I'm basically distributing the sum to each of these. And so this becomes the limit as n goes to infinity of the sum I equals 1 to n, 81i cubed over n to the 4th, minus the sum I equals 1 to n of 54i over n squared. And I have the limit now of that whole thing. Now what else can I do? Well, this property right here says that if you have a constant inside of your summation, you can factor it out in front. Now, what is a constant? This gets a little tricky. A constant isn't just numbers. It's anything that's not an I, because the variable of your summation is the variable I. So for example, right here, I have 81 and I have n to the 4th. Those are both constants with respect to this summation because the variable is I. So the 81 over n to the 4th can be factored out of this summation, and the 54 over n squared can be factored out of this summation. And when we factor those out, we get the limit as n goes to infinity of 81 over n to the 4th times the sum of I cubed, I equals 1 to n, minus 54 over n squared times the sum of I equals 1 to n. So now this whole problem comes down to what is the value of this sum and what is the value of this sum? And for this, we have formulas. Let's bring those in. All right, so here they are, and we are going to use this formula here and this formula here, right? Because we have the sum of I cubed and we have the sum of I. So let's go ahead and put in those values. So it turns out that the sum of I cubed is this formula here. And we won't get into why these formulas are true. Usually we talk about this in pre-calculus. Let's just use these formulas right here. So we can literally replace the summation with this expression. So this becomes the limit as n goes to infinity, 81 over n to the fourth, and that summation gets replaced with n times n plus 1 divided by 2 quantity squared. Minus, then we have 54 over n squared multiplied by this summation. And the summation of I is this formula right here. N times n plus 1 divided by 2. Now we just need to evaluate this limit. Okay, so here is that limit. We have to do a little bit of algebra here. We have the limit as n goes to infinity. We're going to multiply this out, so we're going to square the n, and we're going to square the n plus 1. So that gives us 81 n squared, n plus 1 quantity squared, divided by, and in the bottom here we have 2, actually the 2 gets squared as well, so that's 4 n to the fourth. Minus, and then we have 54 times n plus 1 divided by 2n squared. Okay, so we're just multiplying these here. Now, let's go ahead and multiply all this out, and this can be a little bit tedious. I'm going to do it on screen here. So we have 81 n squared plus 2n plus 1, minus, then we have 54 n squared plus 54 n. And then finally, we will multiply this out. We have 81 n to the fourth plus 162 n to the third plus 81 n squared over 4 n to the fourth minus, same thing here. Okay, so now you have to remember your limits at infinity. When you have a polynomial divided by a polynomial, if you have equal degrees, the limit as n goes to infinity always ends up as the leading coefficient divided by the leading coefficient. So this is going to be 81 divided by 4 minus, and then the same thing happens over here. You have a polynomial, degree 2. So same degree, leading coefficient divided by leading coefficient is 54 divided by 2. So this is 81 over 4 minus 108 over 4. And when you do the subtraction here, you get 27 over 4 negative, right? Negative 27 over 4. So this is the exact area under the curve f of x equals x cubed minus 6x on the interval from 0 to 3. And you might remember just a few moments ago, we had a graph of this function, which looks something like this. And we had part of the area below the x-axis, and we had part of the area above the x-axis. So the fact that our answer is negative here means that indeed we had more area below than we had above. And that is why this area turned out to be negative. Now, this whole process can be kind of intimidating. It can be a lot of work, and it can be sometimes frustrating if you make a mistake, because it is difficult to find where you made your mistake. So you have to be very careful when you do these problems so that you don't have to try to go back and find your mistakes. All right, let's move on to the next thing. There is another way that you can sometimes evaluate definite integrals, and that is by interpreting them as an area of a known shape. So we want to apply that concept here. Suppose you're asked to evaluate the definite integral from 0 to 1 of the function square root of 1 minus x squared. Now, you can see I have the graph here, and you can see that this is the graph of a circle. And so, if I go from x equals 0 to x equals 1, I'm simply finding the area of this piece of the circle. And I think it's sort of obvious that this is 1/4 of a circle. But it may not be obvious why this is the graph at all. So let's go through that process very quickly. So the function that I have in the integral there is the square root of 1 minus x squared. Let's remember that f of x can also be called y. And if I have y equals the square root of 1 minus x squared, I can square both sides of that equation to get y squared equals 1 minus x squared. And then if I add x squared to both sides of the equation, I get x squared plus y squared is equal to 1. And you need to recognize that this is the unit circle, meaning it's a circle whose center is at the origin and whose radius is equal to 1 unit. So if I were to graph that, this is what that graph would look like. However, when you say f of x is the square root of 1 minus x squared, you are only looking at the top half of the circle, because this is a function. And if we look at both halves of the circle, it's not a function because the vertical line test fails. So you're only looking at the top half of the function. Furthermore, in the integral, you can see that we only care about x equals 0 to x equals 1. So when you look at that circle, not only are you only looking at the top half of that circle, but you're only looking from 0 to 1. So you're only looking for this part of the circle. So that is how you can determine that the graph of this is a circle. Now, we still have to actually calculate this. So what is the integral from 0 to 1 of this function? It is the area of this. So we have to know that the area of a circle is pi r squared. So the area of your circle in this problem is pi times the radius, which is 1 squared, which is just pi. However, the value of this integral isn't pi because we only have 1/4 of the circle. So the area in question here is just pi divided by 4. So the value of this integral must be pi divided by 4 because, again, it is just the area between the curve and the x-axis. In part B, it's the same story. We're finding the integral from 0 to 3 of the function x minus 1. This one's a little bit easier because x minus 1 is a line, and it is a line that has a y-intercept of -1 and a slope of +1. So it's pretty easy to graph this function. And then when you find the area from x equals 0 to x equals 3, you can see that you're going to find the area of two triangles. And the triangle on the right will be counted as a positive area, and the triangle on the left will be counted as a negative area. So what's the area of this triangle? So we need to remember that the area of a triangle is 1/2 the base times the height. And for this triangle, the base is 2, it's this distance here, and the height is also 2. So it's 1/2, 2 times 2, which is 2. And then the area down here is the same thing. It's 1/2 times the base times the height. The base of this triangle is 1, and the height of that triangle is 1. So it's 1/2, 1 times 1, which is 1/2. But this area here is negative because it's below the x-axis. And this area here is positive. So the value of this integral is going to be the positive area, which is 2, minus the area below the x-axis, which is 1/2. And 2 take away 1/2 is 3/2. Now, most of the time, you will not be able to calculate areas or integrals by doing this because most shapes are not going to be simple geometric shapes like circles and triangles. So one more concept we need to discuss is the midpoint rule. And it basically says if you want to approximate the area under a curve from A to B, you can do a Riemann sum where you are using the midpoint of each of the subintervals. So again, remember the old Riemann sum usually has an xi star here, and that means you're using a random point, right? And then we know sometimes we use left endpoints, sometimes we use right endpoints. Well, the midpoint rule says you can use midpoints. Delta x is the same formula, and they give you a formula here for the midpoints, but usually it's not necessary to actually use this formula to get your midpoints. So let's take a look at an example. Use the midpoint rule with n equals 5 to approximate the integral from 1 to 2 of 1 over x. Okay, so the important thing here is we're going to take the interval from 1 to 2, and we're going to divide it up into 5 parts. So we need delta x. Delta x is b minus a divided by n, so 2 minus 1 over 5, and that is 1/5. So on your number line here, we're going to go 1/5, so that would be 1 and 1/5, which is 6 over 5. Another 1/5 would be 7 over 5. Another 1/5 would be 8 over 5. Another one would be 9 over 5. And of course, the last one is here, which is 10 over 5, which is 2. Now, to use the midpoint rule, you need to find the midpoint of each of these intervals. So the truth here is that it's probably better to use decimals instead of fractions. So if we know that 1/5 is the same as 0.2, we can rewrite 6/5 as 1.2, 7/5 would be 1.4, 8/5 is 1.6, and 9/5 is 1.8. So let's put those in instead. And then getting the midpoints, you're just finding the number that is exactly halfway in between each of these two numbers. So you can do this, I think, in your head. The number that is halfway in between 1 and 1.2 would be 1.1. The number halfway in between 1.4 and 1.2 would be 1.3. And then 1.5, 1.7, and 1.9. Those are your midpoints. And so to approximate the area using midpoints, you're going to say the height of the rectangle for the first one is f of 1.1 multiplied by delta x, which is 0.2, plus the height of the next rectangle is going to be f of 1.3 times the width of the rectangle is 0.2, plus etc. So this is exactly similar to what we did earlier in this lesson. It's just that now you are using midpoints instead of right endpoints. Anyway, from that point, you would plug all these numbers into your function. Your function is f of x equals 1 over x. So f of 1.1 would be 1 over 1.1, and then we're going to multiply that by 0.2. F of 1.3 is 1 over 1.3, and then we multiply that by 0.2, etc. And of course, to do this efficiently, most of the time a calculator is very handy. And so if you plug all this into a calculator, you get 0.691908. And again, this is the approximate area under the curve using midpoints. The last thing we're going to discuss is some properties of integrals. And these properties will be useful in the next couple of sections. So let's just go through them. The definite integral from a to b of a constant c is c times b minus a. And this is because when you graph this, you get a rectangle, and the area of a rectangle is height times width. The next property says if you have a definite integral of f of x plus g of x, you can take the definite integral of each one separately and then add them together. The fourth property says the same thing, but with a minus sign. The third property says if you have a definite integral of a constant multiple of a function, you can pull the constant out of the integration process. The fifth one says if you have the integral from a to c of f of x dx plus c to b of f of x dx, you can take the integral from a to b. Let me show you why this one is true. So simple concept here, suppose you have a function f of x defined on a and b, and for simplicity, let's say that c is somewhere in between a and b. When you take the integral from a to c, you are finding the area under the curve from a to c. And when you take the integral from c to b, you are finding the area under the curve from c to b. Clearly, this is equal to the area under the entire thing, which is the area from a to b, which is what we have here. So if it's convenient, you can separate your integral at some number in the middle. And the last three properties here are comparison properties. If f is a positive function, then the definite integral of f must be a positive value. Yes, because if f is positive, it is above the x-axis, which means its area will be positive. If f is bigger than g, then the area under f will be bigger than the area under g. Yes. And this last property here I won't actually read to you, but this is a property that is sometimes useful for proving theorems. And then we have two more sort of footnote properties, but these are also very useful. And that is, if you integrate from b to a, you can switch the limits, but if you switch the limits, you have to put a negative sign in front. So you can switch the limits of any integral at any time, so long as you put a negative sign in front. And the final one says, when you integrate from a to a of f of x, that is always equal to 0. And yes, that is because if you have a function and you integrate from a to a, you are simply finding the area under a single point. And there is no area under a single point. So again, we'll talk more about these properties in future sections, but they are worth stating just for the time being. And that concludes this video lesson.